let's talk about the intuition behind using this new way to find the derivative of an inverse. Let's review what Theorem 9.1 and Theorem 9.2 gave us. Theorem 9.1 guaranteed the sufficient conditions for the existence of a derivative of an inverse. First, if a function is continuous, then its inverse will be continuous. So that's nice. But what's even better is that if a function is differentiable, then its inverse is also going to be differentiable, so long as the original function doesn't have a horizontal tangent line. So let's see why this is true. I'm going to let our original function be x cubed, which means that the inverse function is the cube root of x. So x cubed looks something like this. I only care about it close to the origin. And the cubed root of x looks like this. All right, so everywhere that the blue function, x cubed, is continuous, the inverse function will also be continuous, right? It exists everywhere. But what's further, everywhere that I have tangent lines on my cubic function, I will also have tangent lines on my cube root function. Let's just see an example there. Here, at this point, at this x value, I can draw a tangent line to that blue function. I can also draw a tangent line to the green function there, except where I have a horizontal tangent line at the origin, right? For a moment there, the cube function has a horizontal tangent line. And why can't I have a derivative on my inverse? Because if I tried, I would have a vertical tangent line, straight up and down, or a slope of infinity. So the derivative does not exist there. Now, Theorem 9.2 tells us actually how to find these. So this states that I can find the slope of a inverse function at a point by doing this. So let's think about this picture. I can find the slope at this point here. Let's just roughly estimate that's 0.5. So I can find the slope there at 0.5 by taking 0.5 and evaluating it in my inverse. So if I do that, I get maybe a 0.75. And then I can take that number, that 0.75, and I can plug it into the derivative of the original function. So I can find that 0.75 down here, and I can look at my tangent line of the original function, and I get m. So this denominator is just m, and I get a 1 over m. And that's what we wanted to get. So that's kind of the idea here. Okay, let's look at example 9.3. As our example here is going to be x squared. All right, between 0 and 9. Now the inverse, so let me write down f of x is equal to x squared. The inverse function is, it's pretty easy to show, the square root of x. Okay, I think that's all this first part wants. Yep, graph the function and its inverse. The second part asks us to find the derivative of the inverse in two ways. First, by just using the definition that the inverse is the square root of x, and then using the power rule. So if the inverse function is the square root of x, then the derivative of the inverse function is going to be, by the power rule, 1 over 2 root x. All right, but what happens if you don't have the definition of the inverse function? Then you can also differentiate the inverse function by taking 1 over the x value mapped underneath the inverse. And then we look at the tangent lines on the original curve. So if we do this, we get a 1 over, let's leave the tangent lines alone for now, and tell ourselves what is the inverse function. It is the square root of x. And then now, what is the slopes of the original function, well, the original function differentiates to 2x. So this would be 1 over 2x, but evaluated at the square root of x. But I'm plugging in the square root of x into the slopes of my original function. The slopes of my original function is 2x. So I'm evaluating this at 2 square root x. But either way, we get the same thing that we wanted. 1 over 2 root x. So now let's look at a specific point. Sketch the tangent line to the inverse function at x is equal to 4. So here's x is equal to 4. Actually, I want it to be over here. I'm going to push 9 further to the right. Yeah, this just won't be to scale because they need to cross here at 1. So maybe 4 is somewhere over here. All right, sketching the tangent line to the inverse function at x is equal to 4. So I'm with the inverse function. So I want to draw this in green. All right, if we evaluate this, what is the tangent line to the inverse? At x is equal to 4. We end up at a 1 over 2 root 4, or it simplifies to 1/4. So this has a slope of 1/4. The theorem that we just worked on says that I can take my inverse function at 4. I can evaluate it. So what's the square root of 4? I get a 2. And then I could come down here at 2 and evaluate the slope of my original function. And I won't get 1 over 4, I'll get a positive 4.